record. All right, so last lecture, we talked about negative binomial distribution. So here's a quick review of that distribution. So we have independent trials with probability of success P. So each trial basically has a probability of success of P. And our random variable is X, which is the number of trials until we have R successes, right? And that's called the negative binomial distribution, right? So to understand distribution well, it's good to contrast it with the other two distributions that we studied. So in binomial distribution, we have n trials. So this is trial 1, trial 2, ... trial n minus 1, and then trial n. So here we have X number of successes, and the X successes can be anywhere, right? So assuming, for example, X is equal to 2 in this case, right? So I can have a success in the first trial, and then a failure, right? And then a bunch of other failures, and then some success here, and then another failure here, right? So this is an acceptable outcome for binomial distribution. For the case of geometric distribution, my random variable X is X. That means that I'm repeating the experiment X times until I succeed once, right? So basically this is 1, 2, 3, 4, X, X minus 1, and X minus 2. That means that all of these guys are failure. And I only have one success, which is the last one. So basically the goal here is to, succeed once. Once you succeed, you quit the experiment, right? You abort the experiment. And finally, we have negative binomial distribution, which is sort of like a mixture of these two. So here, I want to have R successes, right? So again, assuming that here R is equal to 2, right? So that means that this is my first trial, second trial, third trial, X minus 2, X minus 1, and then X trial, right? So that means that I have, so since I assumed R is 2, that means that I have 2 successes. For example, I succeed in the first trial, and then all of the rest of the trials are failure. And once I succeed again, I stop, right? So basically the importance here is that my success is at the last experiment, right? So my R success, in this case, my second success happens at the last trial. And this is called negative binomial distribution, right? So this is the function. There are more people who have joined since we started. So let me. All right. So for negative binomial, this is the PDF. X minus 1, choose R minus 1 times P to the power R times 1 minus P to the power X minus R, right? So let's look at one example. The probability that the camera passes a test is 0.8. So this is P. Cameras are independent. What's the probability that third failure is obtained in the 5th test, right? So that means that I'm doing 5 tests and my third failure is happening exactly at the 5th test. So this is what's going on here. So 1, 2, 3, 4, 5. So third failure, that means that this guy for sure is a failure, right? And then I have 2 failures here, right? So among the 4 remaining experiments, I have 2 failures, and so since there's total of 4, 2 of them are failure. That means that 2 of them are success, 2 success, 2S here and 2F here, right? So here we say that one important thing is that you have to always remember what you defined as success, right? So in this case, the question says the probability that the camera passes a test is 0.8. And now we are interested all of a sudden in failure, right? So immediately I know that this is P prime, not P. So P is actually 1 minus that, which is 0.2, right? So basically what we want is probability that X is equal to 5, right? So X is the number of trials in the negative binomial. And as I just mentioned, P is 0.2 and R is 3. So all we have to do is to plug in here, right? Any questions? So basically the final answer, let's just do it, will be X minus 1, which is 4, R minus 1, which is 2, and then P to the power R, which is 0.2 to the power R, which is 3, and then 1 minus P, which is 0.8 to the power X minus R, which is 2, right? So that's the answer. So now that I talked about this, I think it's a good place to also prove this equation, right? I'm sure some of you have, already proved it, somehow in your brain. And if you have, that's excellent. If you haven't, that's okay. So let's find out why this equation is correct. I think this is a good example to basically show why this equation is correct. So what's going on is that we are forcing the last basically trial to be a failure. And out of the remaining, remaining 4, we want 2 of them to be failure and 2 of them success, right? So basically I want 2 failures here, 2 successes here, and a failure here, right? So basically what I have done is that I have divided my experiments into 2 sets. One set, the first 4 experiments, and another set, the last experiment, right? And I'm saying that in the first 4, I should have 2 failure and 2 success. So in the first 4 trials, I should have 2 failure and 2 success, right? So now you have to immediately see that, oh, this is a binomial distribution. So that means that in the 4 trials, I should have 2 success. Probability of success is 0.2 to the power 2, and then 1 minus P, which is 0.8 to the power n. So this is here. So here is the binomial with n equal to 4 and x equal to 2, right? And then n minus x, which is also 2, right? So that's the first part. So this is the first part here, right? And then I want the last experiment to be a success. So last trial success, right? So here, remember, success means failure, right? So probability of success here is 0.2, right? And since the question tells me that they are independent, that means that I can simply multiply these 2 guys by each other, right? And if I multiply these 2, my final answer is this guy here, right? Because this is, these 2 terms are the same. 0.8 to the power 2 is the same. It's 0.2 to the power 2. This is 0.2 to the power 1. They add up, it becomes 0.2 to the power 3, right? So I think the proof is important because it tells you, it helps you when you should use this distribution. Any questions? Okay. So there are more people who have joined, so let me admit them. Right. So let's contrast that with another question that is quite similar, but we have to use a different distribution, right? So again, the probability that the camera passes a test is 0.8, and we are interested in failures. So that immediately means that P is 0.2. And we basically want 3 failures to happen in 5 tests, right? So here I didn't say the third failure happened in the 5th test, right? I just said that out of 5 tests, I want 3 of them to be failures, right? So here is clearly a binomial distribution. So this is my X, this is my N, and that's my P, and this is a binomial. So I'm done. Any questions? So let me go back to the previous slide just to contrast it with the previous case. Here I want 3 failures to happen in 5 tests. Here I want the third failure happen in the 5th test. So that means that the 5th test for sure is a failure in this case. But in this case, the 5th test can be a success, right? So I already did the proof. I'm not going to write it down again. So the last distribution before we talk about Poisson distribution is hypergeometric distribution. This one is, in my opinion, one of the easiest ones. You don't really need the equation. It's so simple. So you have basically, you have like a bowl, right? And inside the bowl, you have K objects that are called success. And you have N minus K objects that are called failure, right? So in total, you have N objects, of course. So what you do is that you select a sample size of N, right? You select N of them. And your random variable X is the number of successes, right? So out of these, for example, 5, let's say N is 5, right? So out of these 5 that you have selected, we want 2 of them to be success. So in that case, X is 2, right? So this is the equation for hypergeometric distribution. It's basically K choose X times N minus K choose N minus X divided by N choose small n. So let's look at one example. So we have a batch that contains 100 parts from supplier A and 200 from supplier B, right? So here I can say that I have 100 from supplier A and 200 from supplier B, right? So my N, which was the total number of samples in this case, is going to be 300. If 4 parts are selected randomly, so N is 4 parts without replacement, what's the probability that they are all from A, right? So that means that X is equal to 4 because I want all of them to be from A, right? So all I have to do is to plug into the equation, right? So this will be the answer, right? So 100 choose 4 times 200 choose 0 times divided by 300 choose 4. So it's a perfect place to prove this equation. So what's going on here is that, remember the definition of, I think I have actually an empty. Yeah, I do. So to prove it, we simply have to use the definition of probability, right? So I have 100 parts from supplier A, 200 parts from supplier B. I'm selecting 4 objects, and I want to find the probability, right? So N is 300, right? So remember, probability is a number of, so probability of an outcome. So probability of an outcome is equal to number of elements of that outcome divided by total number of outcomes, right? So first, let's write down the total number of outcomes because that's easier. So total number of outcomes is going to be, I have a total of 300 parts. I'm selecting 4 of them. So that's clearly 300 choose 4. And now I want to calculate number of elements in that outcome, right? So the outcome that I'm interested in is X equal to 4, meaning that all 4 from A, right? So basically, I want all of my 4 parts to be A. Obviously, the number of ways I can do that is 4 choose 100, right? And that's it. That's the final answer. 4 choose 100 divided by, 100 choose 4 divided by 300 choose 4, right? And the solution in the previous slide where we used the equation was the same. If I go back, because 0 choose 200 is 1. Always 0 choose any number is 1, right? Because there is only one way that we can choose nothing, right? So yeah, it's the same answer, but here I didn't use the proof. Any questions? Okay. So what's very interesting about hypergeometric, in my opinion, is the mean of this distribution. So the mean is NP, where P is NK divided by N, right? And let's see if this actually makes sense or not. So I have a bowl with K, oops. I have a bowl with K success and N minus K failures, right? And I'm selecting N objects, right? So I think perhaps it's better to replace numbers instead of N and K. So let's say I have 100 success, like the previous slide, and 200 failures, right? And let's say I'm selecting N objects, right? So in average, I'm going to have the expected value of X, which means the expected value of number, what did we call A and B? I think we called them set A and B, right? So here S is set A and F is set B, right? Number of elements, not elements, probably like number of A parts. So expected value of number of A parts is going to be NP, where P is K divided by N. So in this case, P is K, which is 100 divided by N, which is 300. So that's 1/3, right? So that's N times 1 divided by 3, right? And this does make perfect sense. If you have a bowl where 1/3 of the components are from set A and 2/3 are from set B, and you're selecting N parts, in average, you expect 1/3 of those N's to be from set A, right? So this equation is a very intuitive equation, right? Proving it is actually very, very difficult. In order to prove this equation, you have to use the definition of expected value, where we said E of X is sigma X f of X, right? We have f of X from the previous slide, that long equation, you know, like where the denominator was N choose N. So proving it is very difficult, but the final answer is very intuitive. Any questions? Okay. Okay. I think there's one person who's not muted, and sometimes I hear some background noise. If you could mute yourself, I appreciate it. Okay. So let's look at another example. A list of customer accounts at a company has 1,000 names. Of those, 700 have purchased at least one of the products. 50 customers are randomly selected without replacement, right? So we have a total of 1,000 accounts, 1,000 names. 700 of those have purchased a product, so we call that P, and 300 have not purchased anything. We call that P prime. So we are selecting 50 customers. So N is 50. What's the probability that more than 45 have purchased the product, right? So that means that X is equal to 46 or 47 or 48 or 49 or 50, right? So X has 1, 2, 3, 4, 5 different options, right? So basically, we have to use the hypergeometric distribution. The rest is super easy once we identify the distribution, right? So we plug into the distribution, and as you can see here, X starts from 46 and ends in 50. Now doing this is basically, perhaps you need a computer to do this, because there are, 1, 2, 3, 4, 5 terms in this summation. And some of these are large numbers, right? For example, 1000 choose 50, it's a very, very large number. So unless you have a good calculator, I don't think you will be able to compute this number. So like the numeric number, the numeric answer will probably be like requires a computer. Any questions? So the last distribution that we cover in chapter 3 is the Poisson distribution. So here the random variable X equals the number of events in a Poisson distribution, which is defined by this function, right? So e to the power lambda times lambda to the power X divided by X factorial, right? And lambda is a parameter, is basically the only parameter of the Poisson distribution. So this distribution has only one parameter. If I tell you what lambda is, you can write, basically, you can calculate any probability with the Poisson distribution. You might ask, like why this weird equation, exponentials and all of that? You can basically arrive at the Poisson distribution from the binomial distribution, right? So I will post a very nice PDF on Moodle that proves why binomial distribution in the limit becomes Poisson distribution, right? So basically the basis of this equation is the binomial distribution, and in the limit when n is equal to infinity, so the number of trials that you do is very large, and p, actually my notation is wrong. So when n goes to infinity and when p goes to 0, right? So that means that you have you're doing many experiments. Probability of success in each one of them is very, very small, right? But since you're doing many experiments and you do have, like a reasonable chance of success, because your number of experiments is infinity, essentially, right? So in that case, my distribution becomes the Poisson distribution. So like the proof is out of the scope because there's a lot of algebra in the proof. So we're not going to do it. If you're interested, you can look at this PDF. So this lambda is also the mean of Poisson distribution. So it's the expected value of the outcome. And it's basically this distribution is named after the French mathematician Poisson, who actually proved this distribution from the binomial distribution. And as you can see, it's from more than 200 years ago. So let's look at one example. For a copper wire, suppose the number of flaws follows the Poisson distribution, right? So here we say suppose, but it's not really suppose. In reality, that's the case, right? The number of flaws, in some product will likely follow the Poisson distribution. So this is not really, like a unrealistic assumption. With a mean of 2.3 flaws per millimeter, right? So once you see the mean, you immediately say lambda of the Poisson distribution is 2.3, right? So that means that in 1 millimeter of my wire, in average, I have 2.3 flaws, right? So that means that the expected value of X, where X is the number of flaws, is 2.3, right? In 1 millimeter. Okay. So find the probability of having exactly 2 flaws in 1 millimeter, right? So basically, it's a very intuitive question, right? In 1 millimeter, in average, I have 2.3 flaws. So this is from experiments. I know that I have 2.3 flaws per millimeter. I want to calculate the probability of having exactly 2 flaws in 1 millimeter, right? So we plug into the Poisson distribution for X equal to 2, right? So here my X is 2, and the answer that I get is 0.26, right? So a relatively high probability that I have exactly 2 flaws, right? So like another case that I can tell you is, let's say from historic data, you know that per hour, 50 customers visit Tim Hortons, right? So in every hour, in average, 50 customers visit Tim Hortons. So that means that lambda is equal to 50 per hour. And let's say we want to calculate the probability that, for example, 20 customers visit Tim Hortons in 1 hour, right? Or we want to calculate the probability that 100 customers visit Tim Hortons, in a certain hour, right? So let's say if 100 customers visit, there will be a very large lineup, and the company is trying to, plan for that in advance if, in case many customers show up, in 1 hour, right? So to solve these types of questions, we have to use the Poisson distribution. Any questions?
Sir, I have a question. In real life, how do we find the value of lambda, which is the mean for the Poisson ratio? Do we do it by testing?
Yeah, very good question. Yeah, so I mean, the second part of this course. So in the first part, like I tell you, what are my characteristics of the problem. I tell you, I have a bowl, with a 100 parts A and 200 parts B. I'm selecting 5. What's the probability of this and that, right? So I'm explaining the reality. I mean, basically, I know my system perfectly, and I ask you to calculate the probabilities. In the second part of this course, after midterm, the course will completely change. We will look at real life scenarios, and we want to like in real life, we don't know how many customers visit Tim Hortons per hour, right? So there are different ways we can do them. One of them is to do experiments. You're right. So basically, like we count the number of customers that enter Tim Hortons, in 10 hours, and we divide by 10. We say in average, there's this many number that visit Tim Hortons in every hour, right? Or so in this case, this is beyond the scope of this course, but some distributions are called non-stationary, meaning that with time, the probability changes, right? And the Tim Horton example is one of them, because in the morning, there's a higher chance of, there's more number of people who visit Tim Hortons compared to, let's say, after 10, right? 10 p.m. So these distributions are called non-stationary because they change with time, right? And in this case, if you want to, calculate a reliable estimate of lambda, what you have to do is you have to go to Tim Hortons from, let's say, you have to count the number of customers from 8 a.m. to 9 a.m. for 10 days, right? So you every day you go from 8 a.m. to 9 a.m. and you count, and then you divide by 10, and that's a reliable estimate of the average number of customers who visit Tim Hortons between 8 a.m. and 9 a.m.
That makes sense. Thank you so much.
Yeah, sure. Other questions? Yeah, or for this case, for the number of flaws, we tested many wires, from the company, and we found out, that in average they have this many, flaws. Or you can arrive at this number from theory, right? So let's say that so one of the other things that follows Poisson distribution is the number of radioactive particles, in the atmosphere, right? So some of you guys who are in computer engineering are familiar with RAMs, RAM components in your computer. And the RAMs are called something that they have ECC, error code. I think it's called error code correction or something like that. So the reason that they have to correct for errors is that constantly these radioactive particles hit the RAM of your computer and they corrupt the bits, right? So they convert a bit that is supposed to be 0 to 1 or vice versa, right? So they should have some system to find that out and correct for that. Otherwise, your computer will constantly crash, right? So the number of, it's basically known that in average, how many particles, hit, let's say 1 centimeter square, of space. And that number is also a Poisson distribution. So you can actually compute that from physics because you know that, let's say you're in a city, which is in this altitude, and at this altitude, the average number of this, and my RAM's, size is 2 centimeter square. So you multiply that average by 2 and you get your lambda of the Poisson. So here you arrived at lambda using physics.
That's very interesting. Thank you so much for the thorough response, sir.
Yeah, sure. Okay, so let's look at another case. So this one is a little bit more tricky. So to basically, before we answer this one, let's look at the equation. So here, let's go back. So the definition of the Poisson distribution is here. This is the equation, right? So I don't say it here, but basically one very important fact is that lambda is the average number of successes in unit length, right? So whatever you define as your unit length, lambda is the average number of successes in that unit length, right? So now let's go to the question, right? So in this question, it's a follow-up to the previous question. So I knew that per millimeter, I have 2.3 flaws, right? So I know that per millimeter, I have 2.3 flaws. Now I want to calculate, 2 flaws or, some other number, but instead of 1 millimeter, I'm going to change that to 5 millimeter in the next slide, right? So, intuitively, we can immediately see that since I'm increasing the length of my wire from 1 millimeter to 5 millimeter, I have more flaws, right? Because I'm looking at the larger length, right? So how do we account for that? The first thing we have to do is we have to calculate the average number of flaws per 5 millimeter, right? So in 1 millimeter, I have 2.3 flaws. That means that in 5 millimeter, we have an average of 2.3 times 5 flaws, right? So that's basically the key point. If I change the length from 1 millimeter to 5 millimeter, we have to recalculate lambda. Lambda is the average number of flaws per whatever length you're looking at, right? So if you're looking at 5 millimeter, the average number of flaws is no longer 2.3, it's 2.3 times 5, right? So let's look at the question again. So basically, I want to have 10 flaws, but in 5 millimeter, right? And as I just said, the first thing we have to do is we have to recompute the expected value, right? The average number. In this case, it will be 5 times 2.3, which is 11.5 flaws per 5 millimeter. And the rest is easy. We plug in x equal to 10, which is the number of flaws I'm interested in. So there's one more person who has joined. Any questions? Okay. All right. So in the same question, we want to calculate the probability of at least one flaw, in 2 millimeters, right? So immediately we see 2 millimeters. If I remember, my lambda was 2.3 per millimeter, right? So my new lambda is going to be 2.3 times 2, which is 4.6 flaws per 2 millimeter, right? So in average, I have 4.6 flaws per 2 millimeter. I want to calculate the probability that I have at least one flaw, right? So that means that, you know, X can be 1, 2, 3, 4, all the way to infinity, right? Now, this requires infinite sum. Any ideas what we can do to avoid this infinite sum?
Calculate the probability of 0 flaws and then 1 minus that.
Exactly. Yeah. So sometimes the complement is easier to calculate. So, so the number of flaws that I can have, right? So if this is my entire set, right, I can have 0 flaw, or I can have 1 flaw, or I can have 2 flaws, right? All the way to basically infinite flaws, right? I can't have infinite flaws. So basically all the way to, you know, very large number of flaws, right? So the question wants me to calculate this. Instead of that, I'm going to say this probability is equal to 1 minus this other probability, right, in purple. So, so the first step, we calculate 4.6, and then I say my probability is equal to 1 minus the complement, right? So for X, I plug in 0, right? So we see that this probability is very large. So it's approximately 99%, right? So that means that if I have 4.6 flaws in average, right, there's only 1% chance that I have no flaw, right, in that length of wire, right? So in average, if I have 4.6 flaws, there is a 1% chance that I have, you know, no flaw at all. To be honest, that's a bit lower than what I expected. My intuition tells me that if you have 4.6 flaws in average, I thought there was around like 5% chance that I have no flaws, right? But my intuition was actually wrong. So it's there is 1% chance. So this guy here is 1%, right? So there's only 1% chance that I don't have any flaws. Any questions? Okay. So let's look at another example. The average number of radioactive particles passing through a counter in 1 second is 4. And we know that, you know, as I mentioned, the number of radioactive particles that, you know, arrive, you know, at any, you know, unit area follows Poisson distribution. What's the probability that 6 particles enter the counter in 1.8 seconds, right? So for whatever reason, you know, let's say 1.8 seconds is a critical time for me. You know, like I'm doing some experiment that lasts 1.8 seconds. I want to basically know, you know, how many particles enter in 1.8 seconds, right? So the first thing we have to do is to calculate lambda for this length. So the average number of particles in 1 second is 4. So that means that lambda is equal to 4 times 1.8, right? So that's 7.2, right? So that's 7.2 particles per 1.8 seconds, right? So that means that in average, 7.2 particles enter in 1.8 seconds, right? And the rest is easy. Now I know that my X is 6, and all I have to do is to plug into the Poisson distribution with basically parameter lambda equal to 7.2 and random variable X equal to 6. Any questions? Okay, so 7.2, yeah.
Sorry, to calculate the mean, like, are we ever gonna have to, or is it always gonna be given?
No, I mean, you often have to calculate the mean.
Yeah. Okay. Great.
I mean, which mean do you mean? Like this first mean, of course, is provided, right? There's no way you can find out this mean. Somebody has to tell you. But
Yeah.
you know, the unit length can change, right? So you have to almost always, you know, have to calculate the new mean for the new unit length.
Yeah. Okay. No, it's just because I took a stat course in CJEP, and the guy made us usually calculate that first mean with other obviously he'd give like other pieces of data, but you'd have to plug it in the calculator and it'd take forever.
Oh, I see. No,
So that's what I was asking about.
Yeah.
Okay.
So unless for your project, you know, for your final project here, you know, some average is always provided, like such as this one.
All right. Thanks.
Yeah, sure. So we see that the chance is relatively high, right? There's a 14% chance that, you know, I have exactly 6 particles. Any other questions? Okay. So this is how the Poisson distribution looks like, right? So for lambda equal to 1, right? Yeah, that means that per unit length, I only have, you know, in average 1, let's say, flaw in, let's say, my wire, right? So this is how the distribution looks like. As you can see, it drops very fast, right? So the probability of having, you know, 5 or more outcomes when the average is 1 is, you know, essentially 0, right? When lambda is 4, you know, we can see that the distribution, you know, moves to the right as we expect, right? And when lambda is 10, this is, you know, this is the other distribution that you see, right? So a very cool observation here is that as lambda gets large, for example, 10, the shape of the distribution becomes similar to another distribution that we talked about very briefly. We haven't, of course, covered it. We will cover it, and that's called the Gaussian distribution, right? So for large lambda, the Poisson distribution becomes close to Gaussian distribution, right? And since Gaussian distribution is easier to work with, we often approximate Poisson distribution with the Gaussian distribution. Any questions? Okay. So basically the material, so that was the end of chapter 3. The material that we have covered so far has many applications, you know, of course, in science and engineering, but, you know, beyond science and engineering. So some of you may have watched this movie. I believe Netflix has it, so you can watch it. It's a very good movie, you know, in terms of just, you know, artistic production, but also, you know, it's based on a true story. So I don't want to spoil the movie, but basically for the longest time, you know, general managers were buying players based on, you know, their gut feeling. And then one general manager came and he decided to basically quantitatively calculate, you know, the value of every player based on, you know, some stats, right? So he started calculating some statistics, and he started, you know, basically creating his team by optimizing, you know, those statistics. So I'm not going to spoil the movie for you, but it's a very interesting story, you know, how this turns out, right? So, you know, in your life, if you can, you know, if you see, you know, if you see a problem where, you know, you think that you can basically attack it formally and apply the techniques that you have learned in this course, you know, you can make very significant contributions. In fact, we don't need to go to Hollywood. Right here in Montreal, there's a very famous startup. It's called SportLogic. So what these guys did, they basically started looking at hockey games, right? And started analyzing hockey games, again, based on many stuff that we have learned in this course. And now it's a very successful, it's not a startup anymore. So it has contract with more than half of the NHL teams, you know, basically helps general managers to train and basically do many things. So the basically topics that we have covered so far, you know, their application go beyond engineering and science. Any questions? Okay, so that's the end of this chapter that I wanted to cover. I'm going to stop recording, and then if there's any questions, you can ask.
Sir?
Yeah.